In this situation, we're going to work on an applied optimization problem. And we did some of this stuff in algebra, and we've done this in Calc 1 as well as Calc 2. And normally, once we get to these multivariable problems, we use a process of Lagrange multipliers, right? We use this method of Lagrange multipliers, which simplifies the execution of this problem. In some situations, though, we are able to solve them directly. So we're just going to look at this as our introduction to Lagrange multipliers, which come in the next section. So the problem we're dealing with here is that we have a delivery company, and they deliver, obviously, packages that come in rectangular boxes only. And what we know is that the sum of the length, x, and the girth, y plus z plus y plus z, is not to be larger than 108 inches. We need to determine the dimensions of the largest acceptable box. All right, well, we have three variables here. I'm going to specify x is length, y is width, and z is the height. So if we want to maximize volume, we want to be able to get the most amount of stuff in this box. So the volume equation is V equals X times Y times Z. So right now we have an equation of three variables, and we want to reduce that if possible. So let's think about what our other restriction is. We know that the length plus the girth is not permitted to exceed 108 inches, which means it needs to be less than or equal to 108 inches. So that means that length plus girth must be less than or equal to 108. Well, my length is going to be x, and that girth is the sum, or this kind of perimeter around these edges. So that's going to be 2y plus 2z. And since we want to utilize all of our volume, we want to say this needs to be 108. Now, I'm going to use this second equation. I'm going to isolate x by moving these two terms to the right. And then I can plug that in and create volume in terms of y and z, width and height. So that new equation would be V equals, and for x, I'm going to say x is 108 minus 2y minus 2z. So I have 108 minus 2y minus 2z. And so this accounts for my x in my volume equation. So I've got this x times y times z. And so now I can say that V equals 108yz minus 2y squared z minus 2yz squared. So now I've just created a function of two variables. All right, well, in order to maximize this, we're going to take our partials. So my first step was these equations, developing that equation. Second step is going to be taking my partials. So the partial for V with respect to Y, it's going to be 108z minus 4yz minus 2z squared. Similarly, the partial with respect to z is going to be 108y minus 2y squared minus 4yz. So in order to maximize this equation, we need to set each of these partials equal to 0. And in this situation, we're going to be solving a system of equations for two variables. And those solution values are going to create our critical points. And the critical points are where the max and min values could occur. All right, so setting this equal to 0. So here I've just rewritten, we have our volume function of two variables, y and z, each of my partials, and that should be a y. So I have my volume partial derivative with respect to y, volume partial with respect to z. And as I said, we're going to solve each of them equal to 0. So I went ahead and factored out a z and a y. Now we have two variables, two equations. Looking at this, one thing I would do is I'd come over here and go, well, z equals 0 or 108 minus 2z minus 4y equals 0. Now, talking about the fact that z equals 0, and what I was essentially doing was setting each of these partials equal to 0. One thing we would notice right away is that y equals 0, z equals 0 is going to be a solution. If I let y and z be 0, that's going to zero this out. It'll be equal to 0, true. So 0, 0 is one of our solution points. It's probably not the situation where we are maximizing the volume. So back to this red equation. Now, what I need to do here, I have two equations with two variables. I can use my substitution or elimination method. And in this situation, since they're not all organized and lined up with the same variables, it's easier for me to use substitution. So I'm going to look at this equation. I'm going to isolate y. You could isolate z. It really is arbitrary. But isolating y, I have negative 4y is 2z minus 108, and dividing everything by negative 4, I have y equals negative 1/2 z, and that would be plus 27. So these two y values, I can now substitute this equation of z in for those two y values, and that's going to give me my first y, negative 1/2 z plus 27 times 108 minus 2 times negative 1/2 z plus 27 minus 4z equals 0. So that first factor, I'm not going to do anything with that. And this second piece, distributing, combining like terms, that's going to turn into 54 minus 3z. So again, I have two factors multiplied equal to 0. And now my equations are all in terms of z. So I have negative 1/2 z plus 27 is 0, or 54 minus 3z equals 0. Solving each of those, I'm going to get that z is equal to positive 54 or z is equal to 18. Now, since I know my z value, I can plug z in and calculate y. The corresponding y values here would get y equals 0 and y equals 18. So now I have three ordered pairs. I'm going to scroll back up. I'm going to list these ordered pairs up with the one that I already have. So up here, for my XY ordered pairs, we have 0, 0, we have 18, 18, and we have 0, 54. Now, if I go about this and I let y equal 0 and I set this one equal to 0, basically doing that substitution in the reverse direction, then I'm going to end up with a very similar argument. Here it'll look exactly the same, but I'll get y equals 54. And if y equals 54, then z is going to equal 0. So we'd have this one other point here. So essentially we have 4 critical points that we're solving. And so again, this 54,0, if I had taken this equation, isolated the z and said that z equals -1/2 y plus 27, and I plug it in over here, I get something that is identical to this, but with y's. And so then I would calculate y is 54, z is 0. And then we get that 18, 18 again. So we'd have to do that in both directions. Now, if I look at plugging these 4 values into my volume in terms of y and z equation, each of these terms has a y and a z. So 0, 0, 0, 54, and 54, 0, those would all zero out. They would produce a volume of 0, all 3 of those points. So they're clearly not the maximum. The maximum is going to occur when I plug in 18, 18. And V of 18, 18 is going to create a maximum volume of 11,664 inches cubed. So this is the maximum volume box that we can use or ship. Of course, whenever we do these maximizing and minimizing problems, we always have to show that it is a maximum or a minimum. So our last step here is to use our second derivative test for extrema to prove that this maximum volume, 11,664 inches cubed, is the maximum volume, and it occurs when the width and height are 18 inches each. So now to our last step, VYY, taking that second partial, we're going to get -4z. Again, using this and taking the partial with respect to z, VYZ equals 108 minus 4y minus 4z. And VZZ, that second partial with respect to z twice, we get -4y. So in order to make conclusions, we need our discriminant, and the discriminant is going to be VYY, VZZ minus VYZ squared, or rather -4z times -4y minus 108 minus 4y minus 4z squared. Now we can plug that ordered pair 18, 18 just in down here, or I can plug it into each of these and then evaluate it like that. Either way works. -4 times 18, I'm going to have -72. Evaluating VYZ at 18, 18 gives us -36, and -4y at 18 gives us -72. So essentially we have -72, -72 minus -36 squared, and that value for my discriminant is 3,888. So what conclusions can we draw? Well, the discriminant is greater than 0, and what that means is there will be a max or a min. If it is less than 0, it's a saddle point, and if it's equal to 0, we can't draw a conclusion. So, but because this was a number greater than 0, we know that 18, 18 represents a max or a min. And if we want to prove that it's a max, we need to show that VYY is negative, and that is true here. So because VYY is less than 0, we know it is not a min. There is a maximum. Now, if we recall that x was equal to 108 minus 2y minus 2z, if we plug 1818 into that, we're going to get that the x value equals 36. So the maximized volume is 11,664 inches cubed, and that is when the dimensions are 36 by 18 by 18 inches. And that wraps up this video. As always, email me if you have any comments or questions.